Hello everyone, today I will show the CFD tutorial for the flow over a cylinder. I have the reference here, the prediction of unsteady flow around a square cylinder using RANS. The basic tutorial for the case is to use the steady flow. The unsteady flow I will tutorial for the next video. This is the geometry and this is the mesh. Today I will show you how to do the structure mesh in 2D, and the post-processing we have to do like this. So the square have to be 1 meters of the dimension and at the origin. We will do the steady state, so we will get the post-processing contour like this, like all the above. But unsteady you will get like the wake like this. So let's get started. Today I will use the Ansys Fluent to do an safety. You open the workbench and save the folder. Then you bring the Fluid Flow Fluent into the project schematics. I have used the design roller to create the geometry. So you right click on the geometry and click on the new design roller geometry. Then it pops out like here. So we sketch from the XY plane. Click on the XY plane and click on the sketch. Right now is 3D diagram, so we XY plane we have to click on the set axis on the right bottom here. Please check your units first. On the left top, it have to be the meters. Okay, now click on the sketch and click on the sketching. We have to draw the square, right? So you use the rectangle one. Click here. The constant will show at the vertical line of the origin to be sure that it look like C on the screen, and then you can click and write it here and give the sizing of him. So we use the dimension and get the length or distance on the fourth one here, and click on the two line to get the dimension like here. So we get the L1. You can change the L1 in the left bottom here, change to the 0.5 and we know that the square is the 1 meters, so we get the length of the so you use the general tools to get the dimension of the vertical of the box, V2 to be 1, right? And then the length, it has to be 1 2. Head 3 is 1. Right now you get the square already, square box. So next step is to write the domain. We get the 10D at top, at bottom, and 10D at the inlet, but at the back of the box you have to be 30D. Right now D is 1 because my box is 1 meters. Draw the rectangle again like here and give the dimension again. L4 is 10, right? And the bottom is to be 10, and the top of the box need to be 10, and then the back have to be 10. Oh, sorry, 30. Make sure you get the constraint full of the constraint, because if you get less or more, it will be the trouble. Right now we get the square, the domain already, so we create sketch surface. Like click on the concept surface from sketch here and click the sketch one that we have been drawn, and click on the apply operation. Please add to the frozen, but by the way it is not be different. But here you can use this domain to use in CFD, but you cannot get the structure, or it's hard to be the structure because the mesh didn't get the guideline. So we have to draw the guideline for the image. Click on the new sketch here, and then on the sketch tool we draw the line all the guide for the image structure. Like here, I will use from the corner, it will show P, and then click on the line, and over here you can see the V, that means vertical line. Click here and you will get the line. This line will be the guide one. Do this, like if it pop up at H, it will horizontal automatically. Here, 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 and here. Then I will trim all the over line. Click on the modify and click on the trim, and click on the line that get out of the box here, and you can get the sketch is the yellow line here. You can click on the sketch one, you write the domain, right, and sketch 2 will be the guideline for the image. So we cut the surface by using extrude here, and click on the sketch tool. Change the operation to from add material to slice material here, and then click generate. You will get the surface of maybe 8, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, you will get the 8 surface. So you will see here. Oh, here is the surface body is part already. No, click on the 5 parts, 5 bodies, and grab all, right click to from new part here. That's it. The geometry is already done, so the next step is meshing. Click on the mesh. The mesh look like this. So here we have to get the guideline for the geometry. First, please check the direction of the mesh by using display. Click on display and click on direction here. You can see the arrow that the mesh view generation of the priority of the mesh. So we just know that the direction, where is the direction of the mesh. So if you open the direction of the vector of mesh already, so we right click on the mesh, insert and sizing. We can choose both of the horizontal like this. Click on the edge, right? Oh, sorry, you have to hold the control. Here, like this. Okay, but if you didn't select the edge, you will get like this. It's wrong, so you change to the edge first and then click on the edge, on the horizontal edge, except in the middle like this. Then you click on the geometry from no selection and click apply. Then you will get the like this. We will change the element size to be 0.1 here, and then change the bias type to the first one or the second one, up to you. Bias factor, I will say 10 is maybe the good number. Here you can see that the bias is also to be the direction one, like this line. You can see the direction is on go to the right. The right one will be small and the left one will be bigger. But I want the focus mesh on the box, so I want to be small near the box. Which one is the wrong? Here, like here. So we can reverse bias by select the wrong line. Click on the no selection and click here, hold the control here, click here and apply. Yes, everything is good. Yes. Next step is for the vertical line. Do it the same. Right click on the mesh, insert sizings, and then click edge, vertical edge, like here, here. Yes. Then apply and change the element size to 0.1. Sorry, 0.1. You can see here is equal because we didn't change the bias type. Change to maybe the 1 is okay, and change by factor to 10. You can see which one is not correct. I want to be smallest near the box. This one no. Okay, you can select the revert bias and click on the line, hold control. Here. Okay, so please check again. You keep the all of the line already. Yes. And then we will create sizing again, but this time is to be the smallest length, like here, all the square box. For the example, this one will not be the bias because it will be constrained over the box. You can select here. Oh, sorry. Here. Select it over the box. Here. You can get the 8 edge and change the type to be I would say 0.4. I think smaller here. Okay, 0.04. It will be pretty good, or you can change to be smaller, or 0.025, something like this. Okay, and the last one, you insert the face matching by right click, insert and face matching, and use all the over symmetry plane here. Apply, and you try to generate the mesh. Right click on the mesh and click on generate. You can see here it looks like the structure already, right? Yeah, because we give the guideline of the mesh, so the mesh can be created by the structure mesh. Okay, from this you can create the name section or the name of the boundary condition in here. Click on the edge and then select the okay, click on the left one. This will be inlet. Right click and create name selection here. This one will be inlet, right? Or it have shortcut like right click and create name selection. You can also N, either shortcut on keyboard. This is the outlet, and the top and the bottom is the same. We would say is the domain wall, and the box one be the box. And overall here I will say here this is the fluid, right? So we get fluid. Okay, yeah, we get the surface, right? We get the edge of the box, edge of the domain wall, outlet and inlet already. This end for the mesh generation. Next step is to set up the boundary condition. If you see on the workbench, it will not it's not tick already. We can right click and update it. Yeah, finish it already. So you can check the mesh first. The mesh is about to click on the mesh and statistics. Here we get around 100,000. Okay, and then click on the setup. You can choose double precision and change the call of or the server processing to the 4. This is the student license limit for the trial program. If you want more, you have to buy the license from Ansys, but 4 will be pretty good for this case. Okay, right now it's already opened. First thing you should do in the solver, we call this solver, right? You can check mesh first. On the left top, you can perform mesh check here. Click check and perform mesh check. You can see the sizing of the mesh, X, Y, right? You can see the minimum volume, maximum volume. Yeah, this is checkmate. If something wrong from your geometry, you can change back to the previous one, change the geometry or change the mesh. You can also check the quality of the mesh, evaluate mesh quality to see your mesh is have the good quality of or not. There will be chart of them you can see in the internet. But right now I think we can use this for the tutorial. First, click on the general here, and then we will use the pressure base. That means we are in the incompressible flow. So if you are compressible flow, we will get the shock or shock wave or the high Mach number. You can change to the density base. But right now we use the steady, not transients. So the next video will be transients and how to setting the contour. Next thing, you can change at the top of the ribbon here. Everything is the same like on the left side outline view. This one and this one is the same things. So up to you to change the settings. Click on the physics and check the operating condition. This is the operating pressure, is the default one. It will be okay, right? And next is the model. Viscous, we have changed the viscous. This one we call turbulent model. Like in the papers, you can see in the table here, he used a lot of the turbulence model to compare with. He used standard K epsilon, RNG K epsilon, realizable K epsilon, standard K omega, ST K omega, RSM, LES and EXP. LES and EXP is not range. It's also the upper bound of the computational fluid. LES used a lot more time, and EXP is stand for the real experimental. So we use computer, so this is called range. But right now we will use the standard K epsilon. The default of the program is K omega SST. So we change to K epsilon standard here, and then click OK. And for the material, you can click here and check. We will use the default of the air, like here. Please remember this value we will get to calculate for the inlet velocity by using the Renault numbers. The next one is zone. You can click on the cell zone. Cell zone is the fluid one. This one is the fluid, or the all domain are fluid. If we have the multi-phase flow or the next as one thing, you can see that you will get more fluid, like gas, oil, or something like that. This is just as simple. So the battery one we will should change. You can filter it by click on the zone type here and zone type. Change the inlet first. It would be the velocity inlet. Click edit here. Zone name, inlet, and the velocity have to be which one. The paper didn't say about the velocity inlet, but he say about the Renault number here in the conclusion or in the here. Yeah, 21.4 thousands is will be the Renault number. So to calculate, you can use the internet or by hand. This is the calculator that I have used. You give it the density, you give it the dynamic viscosity that I have shown you in the material, and you put it in the Renault number, you will get the fluid velocity. I will use this to be here. Then I left everything default, apply, check the outlet. The outlet have to be gate pressure at 0, so that means the outlet, the pressure will be equal to the outside of the box, right? And the box one have to be wall. Usually it left it default with no slip, and same as the domain wall at top to bottom. Yeah, it will be no slip at the default. Okay, right now you can calculate it, but how that we know it will be the convert. Convert, that means your result is not changed due to the iteration. So you have to create the report definition or the monitor for lift coefficient or drag coefficients. For right now, you can click on the solution and definition, new, and force report. Click on drag. Change the name to the CD. It will be okay. You will know yourself. It's drag coefficient, right? And click on the zone that you interested in. This thing is the box. Click OK. The next thing is the lift coefficient, right? Create it again. Under the report definition, new, and force, lift coefficients, CL, and click on the box. Please check the vector of the lift again. If you doing like me, I have draw the geometry on XY plane, so the lift would be Y, right? Click OK. Then we use the reference value to be calculated correctly. You come back to the physics and change the reference value here. Compute from inlet. Zone type is fluid, and you can check it again that your reference value is correct. Area equal to 1, right? Density, range. Yeah, so it's okay. Next, we have to check about the method, but right now we don't have to change much or left it default by click in solution and click on the solution method. Here scheme is couple. You can change to same as like the paper. You use simple here. Semi-implicit pressure link equation algorithm. Here you can change to be simple. Yes, and left everything default for the tutorial. And then we should initialize it. It will be the hybrid initialize, so you can see if the iteration get every iteration is small less. I think smaller than -6 is okay. This is -15. So we would run for 300 iteration to check, and then click calculate. You calculate it completely, you can check the residual. Here the residual is not drop enough. The good drop is about to the order of 3. So if you start from 0, you have to be drop until 3. But by the way, you can check the report definition that is steady or not. CD is also like quite steady, but you can run more. For the lift all, this is not the steady, but you can see the geometry. It's not like car or the airfoil or the plane. So if you imagine the flow here, you get the wake here, and it's an oscillation. It would be the unsteadiness. So the lift one will be oscillation of frequency. So you can run more into 1000 iteration. So we add up for 700 and calculate it continually. If calculation complete it again, but you can check the residual is going up and then didn't get dropped from the third order that I would say. So you can continue running or check the report residual, report definition that we create. It will be the oscillation that I was told you, but okay, you can run more, maybe one more 2000 iteration. Okay, right now it's complete it again. So the residual is flat already, but it not drop enough. Okay, this is the tutorial. It depends on the mesh we create. It's not small enough or it's not independent enough that the cost or the viscosity is not, I mean turbine model is used to be, had to use another or something. So you can see the report definition of drag coefficient is the oscillation that I told. So you have to export it, right? Export the plot here and then average it in Excel and the CL2. But when you average it, you have to ignore the starting or the pre-start here because it's not the convert yet. This one is the unsteady convert. So how to export it? You can see at the left on the tree or outline view, you click on the monitors and click on the report plot here. Double click on the CD plot here. You can see that this data, if you mistake to close it, how to open it? You can click here and click plot here. This one will get like this. So where is CDR plot here? So you have to look at your folder that you save. Here you can see on at the file, click on design 0.0 and click on FFF. We are in the Fluent, right? Here CD and CLR file out is here. You can click on the notepad and you will get the graph. You can get all of it to be average in Excel. Okay, and how to do contour? Fluent is also pretty good, but you can do it on the CFD post. Minimize it and click on the workbench again and click on the result. It's open like this. You change the plane to the 2D and you get like this. So you get, click here, box, domain wall. It not show anything, right? Yeah, show just symmetry because it's a surface. So when you want to create the contour, you can click on the contour of this one, and I will get the name of velocity contour. So the variable will be the velocity, right? And the range you can change to the local global. Number of contour, I would say you can change number between 24 to 64, or you want the smoothest, you can select to be 100 or 200. It's up to you. But 11 is the default one. You can see just the 11, I would say 11 colors. Oh, sorry, we have to change the location of box to be the symmetry one. Here you can see the color is feel like the band or is not smooth enough, so you change to 24. It would be better like this. But if you change to 100 or 200, it will be smooth, like this, right? But I would say that if you are in the researcher, if you change the 200 of contour, it will be pretty good, or it will be smooth, it's beautiful, right? But in the research, it's hard to read the value of the color. Since you see the red one to the blue one is very small, so I recommend you change to 24 or 32. It will be pretty good. Here, like this. And of course, in scientific value is hard to read. You have to change to the fixed or the dimension that you can read, or the general one. You change to click on the default legend view. This called legend, right? Click on the legend view and click on the appearance. Change the precision, maybe 2 is okay, and change the scientific to the fixed. Then click on apply. You can see this is easy to read now. Yes. And why is not like the in the paper that is symmetry one? You can see this one is the symmetry, because when we run, you can see on the residual, we stop at maybe drag is not the middle, or it time is like this. You can see, right? It's not the symmetry one. By the way, I think it's useful to let you guys know that this is the how to contour the velocity, and how to do the graph. Like in the here, you want to do to watch the profile of this square. You want to see the velocity profile here, right? What that means, velocity profile? That means you can see on this graph, the figure 10. I will show you that the y-axis, that means the number of the dimension, right? From 0.5 to 1.2. And yes, see my cursor at the center of the square is 0, and the square length is 1, right? So at here, at the top of the square, it would be y equal to 0.5, and we have to draw the line until the y equal to 1.2 to get this line. So that is the guideline for plot the velocity profile. So velocity profile at x over d equal to 0.5. So we are d equal to 1, so x equal to 0.5. We have to create like this. First, click on the location line, and then this is the line of x 0.5 is okay. X 0.5, you will know yourself, and change the line to this one. How? You will know the point, right? This is 0, this is y equal to 0.5, so y is 0.5, and the top is 1.2 as in the papers. X, this 0, this one is 0.5, right? 0.5, so you click on 0.5. Sorry. Yes, and click apply. It will show here, right? And the sample of this line is 10. It will not be enough, so we should do at least maybe 100. It will be maybe is more, but up to you. I will use 100 here, and then we want the expression of u over u0. u0, that means velocity at inlet, so we give it like 0.5 0.512 sorry 0.3125 at the here like this. How? First thing, we have to create expression. On the left here, you click on the expression, right click, new, and we get the, we would call U-bulk 3126 T126 and give the dimension is meter per second here, as in the, how we say this, apply. And what is the U mean? After finish create the expression of U bulk, we have to use U mean. U mean is mean, this one is this not a capital U, is U, it mean velocity U is velocity x, I would say. So create new, I think this is the ratio, so we would say the ratio x velocity is okay. And right click, click on the variable and velocity U here, and divide by U bulk, click right click and expression on U bulk here and apply. You will get the ratio of x velocity here. Back to the variable, right click new and make the variable of ratio velocity x ratio. Click on expression and change to the ratio x velocity that we just made on the expression. Click apply. You get the user defined as a velocity x ratio. Then back to the outline. You get the line already, you get the variable already. Then we will create the chart. How? You can see here, chart. Let's zoom in. It's okay. Chart here. Click on the chart and we will plot the velocity profile here. Click on the data series and change the location to the line that we have been created. The name we will change it later, but the x-axis we know that it would be what would be the ratio, velocity x ratio. So we click on the variable and change to the velocity x ratio, right? And y-axis we have to change to the line or the y here. So click apply. Here is the line that we get. You can see in the papers it look like this, right? If you think it not good enough, for it's not smooth enough, you can change to the 200. But if it's still not good, it's because the mesh is not smallest until you get the point of 200. So this I change 200 is not good enough. This one is called velocity profile. So you will get this line here and you have to compare with the original one or something. But this is how to create the profile velocity, look like this, right? Okay, now you know. So the figure 11 we have to do the same, but right now we want to do right here. We cannot get the curve like this because of the mean of all the steady result of this paper is symmetry, right? You can see this, but our result, back to the 3D viewer and click on the velocity contour, you can see that not the symmetry, it's unsteadiness. So we cannot compare it yet, but you can also want to create a graph look like this, would be great. I will show you, but for caution is not the same. Say you can see here we have to create line first, the line of the back of the square until the number of 9 is okay. Location line center line, I would say center line here from x equal to 1, y equal to 0, right? And x2 is 9. Here you can get the center line here. So let's do it again. The y-axis is u mean. So this capital U, that mean the magnitude of velocity, but the mean one we cannot use it because we just get the output of some time. Mean, that mean you average time already, so it would be the symmetry, but mean is not. But I will show you how. Here expression create the ratio velocity again. Ratio of the max velocity here and velocity mean, I will say variable, and velocity, just velocity, didn't have any u, v or w, and divide by the bulk. Bulk we know that is the 0.3126, right? But in the magnitude, okay, it will be the same. You can type u bulk, click apply here, so ratio will not get the unit, and then you create the chart again. Oh, sorry, you have to variable first, new max will x ratio, and change it to the max velocity here, and click on the chart again. Right now we would say center line max velocity. Again, chart, we change to the location of center line. X would be the x and y would be the velocity, max velocity x ratio here, then apply. So it would be not good enough because of the number of sample. We have to change it into maybe a lot more than 10. You click on the center line and change to 100, it would be good here. So you should try 200 here, 500. Sure, okay. Right now you can see that start from the 0.5 or start from the 1 and you get the velocity like this. That is not the same as here, because here is the mean velocity, so we didn't get it in this video. So just now you know how to expression or create the chart like this. And for your homework, you have to create the average of the CL and CD like this. I will plot it. You can see CL is not, sometimes it's 1.4, right? Sometimes it -1. It will be the downforce. Sometimes it's lift, and this is the unsteady. It will swing. Also, you have to average it, but in the lift, if you average it, it will be 0. I assumption or near 0 because it's square symmetry. But CD would be the constant value, something in the middle of this the oscillation. You can see the sometimes it's 2, sometimes it's 1.7, so maybe it's 2 or something. So you can compare with it in this table that you will got 2, but you use the standard model. This is how to do it. You can do it for yourself or try it for another contour like pressure or the velocity u, velocity y, you can choose it by yourself. Today is then. Thank you for watching.